Okay, so we are live now for this new session of the Continual Learning Seminars series that started a couple weeks ago thanks to the efforts of Continual AI. Today we have the pleasure to host Jujun Shi, who is working on continual learning, and in this particular session, he's going to present his recent work continual learning via bit level information preserving. And if I can say just a couple of words, I think this work is very original, is very interesting, and that's also why it really captured my interest. And I wanted to invite the first hour of this paper to talk about it. I think it can spark some interesting ideas, and I hope we'll somehow open a discussion and with some insights about what we can do apart from normal, benchmarking on standard benchmarks in continual learning. So thank you so much for being here, Yujun, and please go ahead. The stage is yours.
Okay, thanks for the introduction. My name is Shi Yujun, and I'm from National University of Singapore. And I've been a channel of this. I've been an audience of this channel for a long time. So it's a great pleasure to give a talk here. So today I'm going to introduce my work, Continual Learning via Bit Level Information Preserving. It's a joint work of Yujun Shi, Li Yuan, Yunpeng Chen, and Jia Shifeng. So now, what is continual learning? So for continual learning, it aims to enable the artificial intelligence agents to, So continual learning aims at enabling artificial intelligence agents to learn different tasks sequentially. So, and that is different from other settings, because for other settings, normally you have all the data available and you can just train it in an IID fashion. However, for continual learning, your input data stream is normally non-stationary and from different families of distribution. And also what it makes it more challenging is that you cannot access to previous data when you are learning a new task. So that the major challenge of that is obviously catastrophic forgetting. And that's because obviously if you are first learning one task and then you learn another task, and obviously you cannot guarantee that you will have you will preserve the same level of performance on the first task. And empirically, that is normally what happened. However, there is a trivial solution to prevent forgetting, and that is just to freeze the backbone of your model. Like you just freeze every parameters to stay the same across the learning process. And that can definitely prevent forgetting. But the problem is that it will cause a stability and plasticity trade-off, because obviously you will not be able to learn well on new tasks in this scenario. And that's why you have to somehow balance between this kind of stability, which tries to prevent forgetting, and the plasticity, which tries to learn new knowledge. So normally we summarize the previous approach to 3 different types. The first type is what we call the replay-based method. And judging by its name, it's basically you save a bunch of replay samples, and then you replay it when learning new task. However, normally this kind of method is non-trivial because you have to design some more dedicated method than just naive replay data. And also, this kind of method is troublesome because you have to eventually you have to save the data, which causes a linear growing memory overhead cost. And also, this kind of data saving sometimes violate the privacy. And also, another kind of method is parameter isolation-based method. So this kind of method normally divides some kind of task conditional mask on model parameters so that you can know which part of your model to use for different tasks. However, I think this kind of method is not quite elegant because obviously you have to have a lot of routing and condition throughout the execution of the neural network. And this can induce a lot of computation cost. And since for a new task, we have to save a new set of masks, which cause a linearly growing memory overhead. And the third one is actually my favorite type of method, so which is the regularization-based method. And for this kind of methods, they are normally well theoretically motivated and also do not have all the hazard of saving replay sample and having to obtain the task conditional mask. However, the problem of it is that this kind of method will just perform terribly on the normal continual learning setting. So let's first, before we get into introduce the work, let me first introduce some background. So the first background is to view the learning as a process of Bayesian inference on model parameters. So supervised learning can normally be viewed as inferring the posterior of model parameters given training data label pair. And this is intuitive from this relation. So for the left-hand side of the equation, you have the maximum likelihood estimation. And this can essentially be converted to the normal cross-entropy loss, which we use every day for the classification. And also for the right-hand side of the equation, you can simply obtain by manipulating with the Bayes formula for the left-hand side. And then you can obtain the formulation of right-hand side. And for the first term of the right-hand side, you can now see that there is a term that tells you that you are inferring the value of your parameter given the input data D. And for the right-hand side, it's essentially the maximize a posterior V estimation on model parameters. So the purpose of this slide is to give you the impression that the model parameters is not a fixed deterministic value. It's actually a variable that you can infer and estimate something. And the next background knowledge is about the information gain, or in another word, mutual information. So for information gain, also known as mutual information, can normally be obtained in this formula. It's basically the mutual information between random variable A and B is the entropy of A minus the entropy of A conditional on B. So normally we can view entropy of a random variable as a measure of randomness. So the reduction of entropy, in another word, which is the mutual information, is an increase of certainty on variable A after you observe on variable B. Okay, so another thing I want to mention, which is the core to this work, is the chain rule of mutual information. So here, for the left-hand side, please observe clearly that the difference between semicolon and the comma. So here, basically we just view the joint of B and C as one overall random variable. And then we estimate the mutual information between A and this B and C variable. So for this term, it can be decomposed as the summation of two mutual information terms. The first one is the mutual information between random variable A and B. And the second term is the mutual information between A and C conditioned on random variable B. And also please note that for the second term, it's not actually C conditioned on B and A. It's actually A and C are both conditioned on random variable B. And then you estimate the mutual information between A and C. Okay, so how to view continual learning process from the lens of information. So as we have said before, that learning process is essentially inferring the value of parameters from data D. So that being said, when you feed the model with the data D, then your inference result on the model parameters is becoming more certain. And this can actually be directly quantified as a process of gaining information from data. And that is exactly this formula. So for the left-hand side is the mutual information between the parameter theta and the input data set D. And the right-hand side is just a reduction of the entropy on parameter theta. And also, without the loss of generality, we consider theta not as a vector of parameters. We just consider a single scalar parameter because we have to assume that all parameters are mutually independent. Okay, so now continual learning can be viewed as a process of accumulating information from this kind of non-stationary incoming data stream. And the reason is due to the chain rule of mutual information. So we can first look at the left-hand side of the equation here. So for the left-hand side, it's essentially the information provided by all n tasks. So basically, it's a mutual information between parameter theta and the joint of D1 to all the way to Dn. So this can be considered as a oracle setting for the continual learning. We just simply consider that we, at the first stage, we have all the data, D1 to Dn, simultaneously, and we don't have to do continual learning. And so the mutual information between theta and D1 to all the way to Dn is essentially the amount of certainty that we would have on parameter theta. The certainty that would have increased on parameter theta if we jointly train it with the data from D1 to Dn. So now we can decompose it using the chain rule of mutual information as introduced before. So the way we do it is that we view D1 to Dn-1 as one single variable in all. So, and now we can do this kind of decomposition via chain rule of mutual information. So for the first term is essentially the mutual information between parameter theta and Dn conditioned on we have know all the data from D1 to Dn-1. And for the second term is essentially the mutual information between theta and D1 to Dn-1. So the intuitive way to interpret it, the right-hand side of the equation is that consider a two-stage continual learning process. So the first stage is that we learn on D1 to D-1 jointly. And the second stage is that condition on, we have learned on D1 to Dn-1. We have to learn on the dataset Dn. And then throughout the process, we assume that we have some magical algorithm that can just preserve all the information from D1 to Dn-1 that provided on theta before we started to learn on Dn. So that being said, if we have a magical algorithm like this, then this kind of two-stage continual learning is essentially equivalent to the joint training. So we can obviously just recursively expand the second term of the right-hand side of the equation. So it becomes a summation of n-1 terms of mutual information. So this means that after learning the T's task, the extra amount of information that should be preserved is actually the mutual information between theta and dt conditioned on D1 to dt-1. And note that the highlight phrase here is the word extra, because our overall assumption is that right now, before we started to learn on task T, all previous information from D1 to dt-1 on parameter theta has been well preserved. So now we just have to focus on the extra amount of information that should be preserved, specifically to prevent the forgetting on dt. Okay, so anyway, how to preserve this kind of information? So firstly, the first thing we do is that we quantize the parameters so that we can view them in bit representation. And the intuition of doing that is because for this discrete random variable, the unit of mutual information is just a bit that flip with equal probability from 0 to 1. And in that way, we can more intuitively formulate and execute our algorithm. So now we are dealing with the value of mutual information between theta and dt conditioned on D1 to dt-1. So this quantity does approximately tell us how many extra bits have become certain after learning on T task. And the intuition of doing that is still because the mutual information is the reduction of entropy. And the intuitive way to understand entropy for discrete random variable is that how many random bits are needed to characterize the randomness of the random variable. Therefore, the mutual information is thus the reduction of the entropy, which means how many less bits are now required to characterize the randomness. And that being said, how many bits should not flip anymore in this scenario. So also note that the keyword here is the extra, because this is just the amount of bit that we need to freeze in order to preserve the information provided by DT to prevent forgetting on DT. Because we have assumed that all previous information are well preserved, and thus at T task stage, I mean after learning the all previous T task, the total amount of bits that have been frozen is approximately mutual information between theta and D1 to DT. So by recursively execute this kind of algorithm and perform the bit freezing according to the estimated information gain given each task, we can enable the continual learning without forgetting. So, so the method goes like this. So now the problem boils down to how to estimate the information gain. Because as you can see here, this kind of conditional mutual information is a nasty term. And this seems hard to do it. But actually, we have some method. So to start with, we have to record the definition of mutual information. And that is the mutual information between parameter theta and dt conditional on d1 to dt minus 1 equals to a difference of the conditional entropy. And note that the difference between the two entropy terms on the right-hand side of the equation is that the first term does not condition on dt, and the second term is conditional on dt, and condition on more random variables will reduce entropy. So this essentially tells us that how much certain have we become after learning on task dt. So the next thing we do is that we are like a classical work in continual learning community called elastic weight consolidation. It just assumes the posterior on parameters to be a mutually independent Gaussian distribution. So, and that being said, that the precision matrix of this kind of posterior is exactly the diagonal feature information. And with the assumption that the parameter belongs to a Gaussian distribution, we can have a closed form calculation in terms of the entropy of the parameter posterior. And with the entropy terms being closed formally calculated, obviously the left-hand side, which is the mutual information term, can be directly calculated. And eventually, it looks like this. So for this ft term is essentially the feature information averaged over the dataset dt. And for the f0 to t minus 1 term, it's essentially the feature information of the parameter theta averaged over d1 to dt minus 1. And obviously, it starts from 0 because we assume a prior on the model parameter theta. So similarly, we also use this kind of feature information accumulation as the EWC to obtain this auxiliary quantity, which is a feature information. However, differently, we use this to estimate the information gain on model parameter and determine how many bits we should freeze in order to preserve the information and prevent forgetting. So let's look at a concrete example to understand better about what I just said. So as you can see, before we learn on anything, suppose we quantize the model parameter theta to 10 bits. So before we learn on any task, we know nothing about the parameter, so it can be any value. And that being said, all these bits are free to flip. And also from higher bit position to lower bit position is the most significant bits to the least significant bits. And also I give an example underneath. Basically, you can see that to evaluate the value of the theta 0 according to the bit representation, it's essentially the first bit, which is the most significant bits times 1/2, and then all the way plus to 1/2 to the 10. So this is how we execute and evaluate this kind of bit representation. And then we can learn on task 1. And suppose that the task 1, D1, has provided the parameter theta with a mutual information of 1.63, which means the information gain on dataset 1 is 1.63. Then what we do next is that we, according to this estimated information gain, we freeze 2 bits in this bit representation. And also the bits are frozen from higher bit position to lower bit position, because we have assumed that the parameter theta is a Gaussian distribution. And Gaussian distribution is a unimodal distribution, and its randomness is centered around on a continuous interval. And that's why your bits are becoming certain from significant bits to insignificant bits. And then after we have these 2 bits, and that being said,
però
in
purtroppo sono
the following learning process, the value of these 2 bits are frozen, and you cannot change. And that being said, these frozen bits cannot be changed to adapt to new task. And then maybe we learn on task 2, and the information, the additional information provided by task 2 on model parameter is 0.86. Then we freeze 1 bit of information, 1 bit on the model parameter. Okay. And that means right now, after learning task 2, we just recursively executing this kind of bit freezing mechanism in order to preserve all the information provided by previous data. And in this way, we can prevent forgetting and conduct the forgetting-free continual learning. So here is the experiment results. So this is the first group of results, which are image classification results. So we have conducted experiments on MNIST 5, p-MNIST, permuted MNIST, and the alternating CFA 10 and 100, and also 20-split mini-MISNET, and also the sequence of 5 tasks. So from these results, we can see that for our BLIP method, comparing to all these previous regularization methods, because we are more concretely preserving the information, and so we can better prevent forgetting comparing to these methods. However, although comparing to some task conditional methods such as HAT, which has task conditional mask on model, although, for example, for the alternating CFA 10 and 100, it do not have the same level of performance. However, for HAT, it rely on a linearly growing memory overhead, which is not desirable. So that being said, our method can prevent forgetting better than regularization method, but free from all this hazard and the redundant of replay buffer and the task conditional mask. And also, I would like to highlight here that although this method frees bits task by task, but it does not store any task-specific information, because everything we store is that, for example, up to current stage, like up to T task, how many bits have we frozen in total, or what is the cumulative feature information? So no task-specific information is saved. Only this kind of cumulative auxiliary terms. So our memory overhead is actually constant. Okay, so now it is the continual reinforcement learning setting. So in this setting, we just continually learn to play 6 arterial games in the order from left to right and top to down. So for the green line, it is essentially the reward curve of our method BLIP. And for the orange line is the curve of EWC, and for the blue line is the naive baseline of naive fine tuning. And for each game, for each environment, we train for 1 million environment steps. And as you can see, for the first figure, so from 0 to 1, obviously all methods just the reward just increase simultaneously. However, from 1 to 2, after we started to learn on task 2, obviously the fine tuning baseline just degraded catastrophically, and also our method BLIP and the EWC decreases at the same level. However, as the continual learning proceed, like from 2 to 3, which means when we are learning the third task, James Bond, then for the Kung Fu Master, the EWC method just forget catastrophically, and for our method, it can maintain the same level of performance throughout the whole process. And the same phenomenon can be observed for the environment of boxing. And also, for the right-hand side, it's basically a summary on the accumulative normalized rewards. So, basically, we just normalize the rewards of each environment to 0 and 1. And for the catastrophic setting, eventually, after learning all environment, it should be approximately around normalized reward of 1, because eventually throughout the whole process, you only preserve your performance on one single task, which is the task you just learned. And however, for an ideal model which can simply preserve forgetting throughout the whole time and concretely learn everything, it should end up at the reward of 6 at the final step. And obviously, as we can see, the green line, which is the accumulative normalized reward for our BLIP method, it is consistently above the line of EWC and fine-tuning baseline. Okay, so here is a concrete video demonstration of the whole process. So for a matrix of GIF, the I row J column GIF is essentially how your agent perform on J task after learning the first I task. So for the first GIF of the EWC and BLIP, obviously both agents can learn to perform well. So basically, the first game is just your enemies coming from different direction and you beat them all. And obviously, they can both do well on these tasks. However, as your continual learning proceed, for example, when you're finished learning the James Bond task, however, the EWC agent just simply sometimes forget to react, like this one, forget to react to the attack of enemy and eventually die. And however, for our BLIP method, although sometimes it also will forget how to react, however, it can still manage to get out of this kind of stalked situation and try to fight back. So, which means that it can still perform well on the first task. And also, as you can see, for the third GIF, it is essentially at the same level of performance, which means in this 3-task continual scenario, you will not have the problem of stability and plasticity trade-off, because it can not only prevent forgetting, but also learn well on new tasks. However, that is the problem is not the same when we are learning 6 tasks in a continual fashion. So the major problem of this method is still that it does not address the problem of stability and plasticity trade-off well. Because as you can see, for the last 3 figures, as learning proceed, although the BLIP agent indeed prevent the forgetting on previous tasks well, but it cannot learn well on the new incoming task. For example, as you can see, the green line is consistently below the line of the EWC, which is the orange line. Although, as we have showed before, for the overall accumulative accuracy rewards, the BLIP is better. However, this still means that it has a major problem that needs to be solved, which is the stability and plasticity trade-off. So, so the intuition is that as training proceeds, there will be less and less free bits to use for learning new tasks because you have to preserve the information provided by previous task and prevent forgetting. However, what if we can actually, just squeeze the information and so that we don't have as much amount of bits to freeze per task after learning previous tasks. And this means that we will have more capacity or more free bits to somehow learn to adapt new tasks, which means that it's possible we can address the stability and plasticity trade-off in this sense. So, and this actually connects to the viewpoint of wide minimum, because as have been elaborated in the work of understanding the role of training regime in continual learning before, wide minimum is obviously beneficial for continual learning, and this image is stole from their paper. So obviously you have when after learning the first task, say you end up in a local minimum W1. So for the green line, it's actually a sharp minimum. However, for the blue line, it's actually a wide minimum. So obviously, as you shift your parameters to W2 as you are learning the task 2, because the blue line represents a wide minimum, because it's actually very wide, so the loss curve will not increase sharply. So the amount of increase in the loss of task 1, which is forgetting, is significantly less than the increase of loss of sharp minimum. And actually, you can eventually show that as long as you assume your training regime is a quadratic loss function, then this kind of forgetting can actually be bounded by the nuclear norm of the Hessian of the optimization landscape. So what does this kind of work has inspiration on our information viewpoint? And that is because although it has not been mentioned in our community, but for generalization community, this kind of wide minimum has long been connected to information in weights. So because normally people believe that the wide minimum, which is a flat minimum, means the model contain less information about the data. So under some assumptions about the posterior on the model parameter W, the paper emergence of invariance and disentanglement in deep representation can actually gives this bound. Although this is not the main result of the paper, but they give this bound. So for the left-hand side of the equation is obviously the topic of today, the mutual information between parameter theta and D. And for the right-hand side, the important term is the second term, which is the log nuclear norm of the Hessian. So it basically means that if the nuclear norm, the Hessian of the Hessian is small, then the mutual information between parameter theta and D is small. And obviously, in our case, it means this. So if you have a wide minimum, then obviously it results in a smaller mutual information between parameter and D data. So it means that you have, for each task, you have less bits to freeze in order to prevent forgetting. And that means you will have more free bits to adapt to new tasks, and you can learn better on future new tasks. And that means you have a better stability plasticity trade-off. So let's sum up about this talk. The first one is that we proposed a novel continual learning method via quantization and bit freezing. And according to our understanding, I think this is actually the first work that proposed to rely on quantization and the scheme of bit freezing to formulate and conduct continual learning without forgetting. And the second one, which is actually the one I want to emphasize most, is that to the best of Uh, sorry. Can you hear me?
Yeah, yeah, now we can. You got
Oh, okay.
disconnected for a second only.
Oh, yes. Sorry. I have to share again, right?
No, we can see actually the screen.
Oh, good. Okay, sorry. Okay, so this is the second point is actually the one that I want to emphasize the most. It's because although this has not been explored before in our continual learning community, but this is actually kind of important quantity in the generalization community. Uh, Actually, there's a body of literatures that leverage this mutual information between parameter theta and theta d to characterize the generalization error. So my point is that maybe starting from this point, we can, based on this quantity, we can connect the continual learning and the generalization analysis, and we can do some more rigorous generalization analysis in the setting of continual learning. And also, obviously, there are some further improvement room and follow-ups that can be done via the connection between the wide minima and the mutual information between the parameter theta and the dataset D. But unfortunately, I haven't got time to actually try it. So that is just left for future work. So the code of our work is now public available. And for any questions, and if you want to discuss anything, just please contact my email. So that's all about today's talk. So thanks for listening.
Thank you so much, Eugene. I think it was a
Thank you.
great presentation.
Thank you.
Do we have some questions from the audience here on Microsoft Teams or following us on the live stream on YouTube? Let's see, I'm trying to managing a couple screens here. So, maybe I can start with a simple question. You said that there are these interesting and possible future connections within these wider minima and your methods. And so, are you actually working to make these let's say because this connection and build on top of what you have experimented here? And especially, do you see some, let's say, interesting scalability, let's say, improvements that you can make on this, or do you see some, let's say, issues in doing that?
Yes. So a major problem about this quantity, the mutual information between parameter theta and d, is that uh, in practical scenario,
Ah,
you can't actually estimate that because you don't have the posterior on parameter, and
mm,
all your parameters will not be mutually independent.
mm,
And to actually concretely estimate this term is actually very troublesome. So in this work, we have to make some many assumptions and on this quantity so that we can operate on it. And also, as for the connection to the generalization literature, actually, I'm newbie in the community of generalization because previously I don't know much. Actually, I just started to read papers. So, but from my standpoint, is that normally it's very hard to actually calculate something, to actually have a very concrete bound on the generalization. It's normally some abstract term like the mutual information between parameter theta and d. So only for some very simple toy models such as Gaussian, like the binary Gaussian model, which is the work of one of my friends. You can write some closed form uh, expression in terms of the generalization error. So I think it's still quite challenging to actually build this kind of, although there's a potential, but it's still quite challenging to build this connection. Consider the fact that in the continual learning setting, you're not dealing with one simple distribution. You're dealing with actually maybe multiple distribution along the way. Yes.
yeah. Another question that I was um, thinking right now. I mean, it shouldn't be so hard to implement these in code, right? I mean, you offered your own implementation in your GitHub. I have not seen it, but I was wondering how let's say, troublesome is to implement these, and possibly also, do you have some insights about the complexity in terms of runtime that this may have?
Okay. So normally, the actually according to my experience of running the program, the overhead is actually not much because essentially the only uh, overhead is I think is that after learning a task you have to freeze bits, but actually this can actually be done by some efficient parallel executing in the PyTorch library. And also another thing that might cost time is the quantization aware training. So one thing I didn't mention is that for the parameters, we are quantized it to discrete values, and we have to use the straight through estimator uh, to somehow estimate the parameter. And you have to like register a hook on the gradient propagation function. But according to my experience, that's actually not that time consuming. It's actually very fast. Yes.
Cool, cool. Thank you so much, Eugene. And
Okay.
so, do we have any
Thank
more
you.
questions from the audience? Okay, yeah, yes, we have one question in the chat. Uh, okay, is Amati. Thanks for the insightful presentation. Assuming that you
Thank you.
need a CNN for those experiments, do you observe which bits were first preserved in terms of layers, abstraction level, um, after going through the first set of tasks? Did they
Yes.
align with the observation from a previous work that says forgetting mainly happens in the final layers towards the output of the network? So in that case, we would need to preserve bits for older tasks, mainly in the final layers, and let the initial layers maybe be shared. What do you think?
Yeah. Exactly. This is actually what we have observed in our experiment. Actually, there's a visualization. I think
Ah, nice.
in the last section of the paper. So basically, we just visualize a heat map, and each pixel of the heat map is that how many bits have been preserved for the parameters, and also
Nice.
but the visualization in the main text is actually just the last layer. So we have some results that we have done for the first few layers. And the observation is exactly like what he just mentioned. And also, I think mentioned in some of the other previous continual learning literature that normally we just have to share the initial first few layers. So for the first few layers, the bits just the amount of bits just quickly got frozen, and actually is several layers in the last several layers that have the ability and the freedom to update for new tasks.
Yeah. Perfect,
Yep.
perfect.
Thank
Thank you again, Eugene, for your presentation. I hope you will follow, let's say, these research lines, and
thank you.
possibly also add these new great algorithm to our collaborative library Avalanche that is trying to
Yeah,
collect, and reproduce results in this area. So I hope that you get the chance to do that. And
thank you.
I thank you all for being here today, here on the Microsoft Teams, and also following us live on YouTube. I just remind you that we do this every Thursday at the same time. And so let's see each other again next Thursday at 5:30 p.m. CEST. Thank you so much, and have a nice
Okay, thank
evening
you.
and a day.
Yeah.
Bye.
Okay, thank you.
Bye.
Bye. Bye.